Hello everyone. And since I just found my last Friday's recording disappeared again, so here I just want to use this new video as a backup video to help you understand what you need to do in this lab 5, and hopefully it will help you. Okay. So Lab 5 is for the binary BPSK modulation. What is modulation? I think the first paragraph has explained it very well. Modulation is the process of converting a baseband low frequency signal into a signal with high frequency components, so that we can transfer information across physical communication channel. So yeah, so the most important reason why we use modulation is we want to convert a baseband signal into a high frequency signal. But yeah, another reason is that if we check this formula, this is the wavelength formula, and the wavelength equals to the speed of light over frequency. Speed of light is a very big number, right? And if your frequency is no, which means your wavelength is very long. So in our circuits design, if your wavelength is long, your antenna should be also long. But that's weird, right? If we generally you can't just carry a very long antenna to transmit your signal. What you want to do is just carry a small cell phone to transmit your signal. So that's why, since you can see in our cell phone, the antenna is very short, which means the transmitted wavelength is very short. So the transmitted frequency should be very high. That's why our modulation just converts the baseband signal into a high frequency signal. So you can see, yeah, that's the reason. Okay. No. Firstly, our signal is just a discrete signal, which only contains 0, 1, 0, 1, 0. But we need, for example, Bn is 0, 1, 1, 0, 1, 1. And then we just convert the 0 to -1, convert the 1 to the +1. So after that, we should make it to be continuous time signal. For the continuous time signal, every bit occupies t seconds. So you can see this is the -1, +1, then +1, -1, +1, positive. So you can see this wave should be our transmitted continuous time signal, be tide of t. After that, we did we need to multiply this baseband signal with the cosine function to make it to be a high frequency signal. So this omega c is the reading, and since we know omega c equals 2 pi times fc, so this fc should be this fc is the carrier frequency. So okay, that's how it works. Okay, it's just to show how it will work in our MATLAB work. Okay. Okay, you can see here I just define I just define 25 bits here and use the BPSK modulation, and for the bit duration to bit duration is 0.001, and here is RC. RC is the symbol rate. It's the 1 over bit duration. So RC should be 1000 hertz. 1000 hertz. Okay. And you can see for other parts, I think you should be familiar with this. Oh, for other, FC is the carrier frequency, and RC is the radio. Oh, is the phase. Oh no way. Sorry. I should call it a symbol rate. RS. RS is the symbol rate. RC is the phase, and the FC is the sampling rate, and omega c equals to 2 pi times fc. Okay, so here is since there are 25 bits, every bit occupies 0.001 seconds, so the total duration should be 0.025 seconds. So it's correct. Okay. Now, what we need to do? What we need to do is to multiply our baseband signal with the cosine function. Here, the modulated beat is the beat height of t. So this is just the baseband signal. Okay, let me see. Okay, oh my god, this is just all blue. Since our carrier frequency is very high, so which means the variation should be very fast. So here you can just what you just say is all blue, but if you just use a lower carrier frequency, for example 1K, you can see the obvious variation, phase variation. Okay, so let's go back to 100K there. And the next thing is just use our previous frequency analysis tool to analyze this, to analyze our baseband signals frequency representation, and to analyze our transmitted continuous time. What I mean is that to analyze the BPSK modulated signal to see what they are looking like. Okay. So the third figure is for the representation of bit height of t. Bit height of t, the baseband signal. Since I have introduced And the baseband signal should have the maximum frequency of the maximum frequency of 1/t. Here, it should be 1000 Hertz. So you can see according to this frequency representation, most information is located on this range. And of course, there are some other information is located on the higher frequency range. But I think most important part is this part, right? And you can see, according to this frequency representation of BPSK modulated signal X, actually, you can see it. Okay, let me return to the. And this is a representation of the baseband signal. If we just multiply the baseband signal with the cosine function, cosine of omega c t plus phi, so you can see there will be two peaks, which are located around minus FC and FC. So since the cosine, you have learned the Fourier transform of cosine function. So cosine function that will shift the frequency representation of signal to the left and to the right by F. So here F is the FC, so you can see, and there will be two peaks here. But you can see, suppose our baseband signal, the frequency representation have the magnitude of 2, and after multiplying with cosine function, these two peaks will have the magnitude of just 1. So it's the half of the magnitude of 2, right? So if you want to make they have the same magnitude for each peak, you should attempt 2 here. Okay. Okay. So what I want to say next, you can see according to what I have explained, for the BPSK modulated case, after multiplying the cosine function, the baseband signal should be shifted to the left to the right by FC. So here you can see, here is FC. That's correct, right? Okay. So let's see. Let's see what we need to do. Oh, we need to demodulate that. For the part 2, what I want to say is that generally the transmitted signal will go through some kinds of channels, such as AWGN channel and ISI channel. ISI means the intersymbol interference channel. But in part 2, we just assume the channel is perfect, which means there is no noise, there is no ISI. What you will receive is what you is perfectly matched with what you have transmitted. So let's just assume there is no noise and there is no ISI. Okay. Then what you need to do, or what we need to do. Okay. Let's go back to here. Demodulation. Oh, what's that? Demodulation. Firstly, we should multiply xt with the cosine omega ct plus 5. And this omega, this xt is the transmitted, is this one. It's just our transmitted signal. So why we do this part? Since if you check this figure, this is our xt. Since the cosine function is just to shift the signal to the left, to the right, by fc, right? In the frequency domain. So if we just shift this two peak to the left and to the right by fc, you will see there are 5 peaks here, and they are located around minus 2 fc, minus fc, 0 fc, and 2 fc. You can see we don't want this part, since at the receiver we want to process our baseband signal rather than high frequency signal. So we don't want this high frequency information. We just want to remove it and keep this low frequency information. This low frequency is corresponding to our baseband signal. So how can we achieve this? We just design a low pass filter, and that only cover the low frequency information and remove high frequency information. So that's what we need to do. Okay. So apply a low pass filter HT to X1T high frequency interference. Okay. The B height of T is an estimated of B height of T. Okay. How to design the filter? Here, it has show some steps of designing this low pass filter HT, and you should read this part, since it's I don't think it's tricky, but it's some kind of, you need to do some calculation to use the right parameter. Since according to this introduction, 1 is corresponding to half of sampling frequency, and so what omega n you should choose is the corresponding to your cutoff frequency. Suppose there's omega n, my cutoff frequency. So firstly, we should decide what cutoff frequency we should choose. Generally, we can just choose our maximum frequency as our cutoff frequency. In this case, since our maximum frequency is 1000 Hertz, so we can just choose the cutoff frequency as 1000 Hertz. So here we can see if here is equal to 1000 Hertz, so omega n should be Okay, this is part of FC, and this is 1000. So just to use this equation, you can see in my MATLAB. I just cut off is 100. This is omega n, and just H is my filter, and then after design this filter, you just convolve. Oh, okay. You just convolve HX1 with this filter. Then this is my B height. It's easy, right? Okay. Just show. You can say this is just my magnitude response and phase response of my filter, and this is my final result. You can see this is the original baseband single, and this is my estimated single B height. Sorry, this should be B height of T, and this is yeah, you can see it's not the same. You can see there are there are slopes at this boundary, right? At this boundary. At this boundary. But usually you don't determine your bit information at this boundary. You to determine the bit information, you should check this central points rather than the boundary points. So since at the central points, I think they're perfectly the same, right? Okay. So this third figures and the fourth figures are for the frequency representation of the B height of T and the B height of T. So you can see, I think they are the same in these two figures, which means I think my operation is correct. I hope when you are doing this part, and your final frequency representation of these two signals will be the same. Yeah. Okay. So for the part 3, I think that's left to you to finish. But I will also cover it in our later class. Since if I find many of you have problems with have questions about the part 3, maybe I will discuss this part 3 at our class, and to help you make it easier for you to finish. Okay. Thank you.